Well, here we are once again. It's the physics video lecture. Physics 107B video lecture 2. So we're moving right along in chapter 7. We had Ohm's law and related stuff. Today we're going to talk about Faraday's law. And we start off with introducing the concept of the electromotive force. So yes, electromotive force, also known as EMF, force, and it's a line integral, say around a closed circuit, F dot dl. And as the other day, we have F as force per charge. And so you can see the dimensions here are going to be work per charge, force times length per charge. So work per charge. And in the simplest case, maybe not a closed circuit, but a line integral from one end of a battery to another. We'd have its electromotive force as a result of the electric field times dl, which would give us that voltage difference. Okay, so I'll go ahead and put that here. Example, ideal battery. So without any internal resistance, that's just going to be the voltage A to B E dot dl, for instance. Okay. Now, we have a homework problem in which we have a battery with an internal resistance. So I'll go ahead and sketch that. There, the idea is that you've got enclosed in the battery, here's A and B. Intrinsically, you've got a voltage, but also voltage drop, but you've got a resistance here, lowercase r, internal resistance. So if you hook that thing up, our homework problem had us talking about the power to a variable resistor. And in that case, you cannot adjust this. Okay, so this is the one that's adjusted. You're going to maximize the power output or something like that. Yeah, what problem was that? Problem 7.5. Okay. So there's our electromotive force. And what we're going to do is an application of this with a system that's in motion. It's going to be called motional EMF. And this is an interesting little system. Okay, so the idea is going to be, as we'll use some colors here, we've got a magnetic field restricted to a certain area, and we'll just have it be constant and into the board like this. And now we have a loop of wire in motion. So black is fine. And this thing has some resistance as one of its properties. So that's a loop of a conductor, and this whole thing is moving to the right with speed v. Okay. Moving to the right with speed v. This is B into the board, and restricted right there. So we'll work with this a couple times. This first time, let me see, I gotta label the separation here as a length h. And where is this force per unit length operating? On this segment here. I'm going to show in a minute that it's going to end up giving us a clockwise current. Okay. So the force, so I have everything right here. It's a loop, conducting loop, moving to the right with speed v. Got the resistance, that's good. So, good, let's go ahead and write down this EMF in the motional case. So, we're looking at just a magnetic force. So, force per charge would just be V cross B dotted into DL. And your V, so those are the charges, charge carriers inside this conductor. They're moving to the right, okay? You cross that into B into the board, and you're getting a force upward per charge, and formally it's a positive charge, so we're going to get a clockwise current. So that produces a clockwise current, and it's only along H that you're going to get the contribution. These two would cancel. And therefore, so the force on the, because, well, this one I already showed, if you have a force here on that charge, it's, you know, in one direction, down here the other, so that's not actually producing a current. It's a current through the conductor. Good. So what do we have here? We've got V, and then we've got B, and we've got H. So that's the motional EMF, and I'll just write current clockwise. That's the first result. We'll number these things. The next thing is, now that we have established that current, we now have a current in this conductor, and it too is going to experience a force. So the force on the current carrying conductor, on the conductor itself, we're going to have to do that with a dF, and then integrate, yeah. Yeah, I'm calling it D force I dl cross B. Okay, so let's look at that for a moment. This thing is moving to the right. Okay. So we have I dl cross B. So this thing crossed into the B field. That's pointing to the left. So there's a force to the left, and again we just integrate it along this thing, this length H there. So we get F equals I H B, simply from integrating this thing up across that length H. And again, this is the only contribution, these two cancel. Good, so we have an EMF, electromotive force, and we have this actual force to the left. Good. So yeah, we're feeling some force as we push this thing, and we now remember that power equals force times velocity. So the power in this circuit, or not the power in the circuit, I'm getting ahead of myself. The power that we're expending to push this thing is going to be this F times V, and we have I H B times V. But look at that. That is the electromotive force itself. So that is I times E. That's the power to push the thing. What about the power in the circuit? Power in the circuit, for example, this is a generator after all, so if this were a light bulb, then our power would also be E equals IE like that. And of course, Ohm's law would, we're reminded that we have this relation there. So that's where the resistance would come in there. But the point is that this is actually a generator. Probably hard to make it work in real life, but in principle, this is a generator. As long as we have some of this magnetic field, as long as we're in that area, we're pushing against a physical resistance, we're doing work, and that work is literally being converted to the work per unit time, the power that is being dissipated in that resistor there. So this little theoretical object here is a generator. We generate power that way, and we're just also just seeing conservation of energy because we're converting mechanical work into power to say thermal energy in the circuit. Okay, that's a great example. So we're going to do another analysis of that circuit. I'll send this up. And I'll just start out fresh and draw a new one. Redraw this one. But yeah, further analysis of the same circuit. I'm just going to redraw what I have there and continue on. So what should we call this here? Okay, same device. We're going to look at the magnetic flux, which we're going to call phi or phi sub b. So this time I have to draw the same thing I had. We've got our B field into the board. That's enough X's. And we have our circuit again. Still this way with speed V. This time, and okay, it's all magnetic flux, V into the board. This time, we consider that the area of magnetic field ends right here at the dotted line. So there is a length X here. And we know the magnetic flux is just the field, which is pertaining to be constant, the field times the area. Okay. So magnetic flux phi sub b is equal to the integral over that surface there, surface, or should I call it area, one or the other, b dot dA, like that. And this, in this particular case, is just, I'm still calling this H here, B times H times X. So that's the magnetic flux, but since this is moving forward, of course, it's changing in time. Magnetic flux, we have star here, d phi sub b dt is equal to b h dx dt, okay? But dx dt is going to be minus v because this x is getting smaller and v is positive in this direction. So we get a minus sign bh times v. And what we see when we compare these and the expressions we had up there a moment ago, so that what we have is e phi dt is equal to minus that EMF. So this one really deserves to be showcased. That would be Faraday's law for this particular system here, for motional EMF. Okay, so the flux rule for motional EMF. Flux rule, motional electromotive force. I just mentioned Faraday, even though we hadn't quite gotten there yet, because it turns out that this is very general. So you don't just have to have this system here, where in fact, and we analyzed it just with this, with the basic laws of forces on charged and magnetic fields and currents and the like, but rather what Michael Faraday found in this series of experiments is that any way you change the flux that you can think of, you're going to generate a corresponding EMF. So I'll just put down a couple of those just to be concrete. Here what we did was we just changed the amount of flux going through this loop by making the loop smaller. So there are other ways as well. Let me first write this down. So Faraday discovered that, and you know, you've seen those in your experimental lectures. Faraday discovered that any change of phi sub v resulted in some corresponding EMF. And when you're playing around with these things, you can just do an example. So suppose you have something similar to this. You've got a loop of wire and you've got your G field. You can do a number of things. You could increase the strength of the field. You could decrease the strength of the field. You're going to get an EMF and therefore generate some kind of current in here. But you could also take the loop and physically twist it so that, you know, you've got the flux. Got something here. Yeah. So you've got the flux here. You turn the loop perpendicular, and now the flux has vanished for that reason. We're talking about generators. You know, that's one way to do it. So you can turn the loop and change the flux. You give it another turn, and now you've got the negative of the flux you had before. You can deform the loop by squeezing it or stretching it and so forth. So any change. So examples, let's just list some. B increases, decreases, or decreases, or change the orientation of the loop. Okay, so you can change its orientation, and then I'll say you can change the shape. in such a way as to change the surface area. Shape slash surface area of the loop. And you're always going to get some corresponding electromotive force out of that. And this example also shows there's going to be work involved. Okay, so you're not going to get it for free. There's going to be some work involved, and if it is hooked up to a circuit, then work will then, over time, will be some power. Okay, so there's the flux rule for motional EMF. And the next thing to talk about is the direction of the current. Now this example, the direction of the current was very easy because we just took rectangles and perpendicular fields. The direction of the current was easy to ascertain. In these other cases, it can get a little more complicated, but fortunately there's a really simple principle that allows us to find the direction of the current. Direction of the induced current. And I'll actually just use that model up there again. So the rule, I should have left that one up now that I think about it. So let's call this direction of the induced current. Question mark. What we have is this. We have a change in flux which results in an EMF which results in, if you're in a conductor for instance, a current. But that current that's been produced produces a magnetic field. Induced B field. Okay, so we didn't actually look at the induced B field on our model that I just erased, but the principle is that this induced B field opposes the change in flux. So this is the principle here. The induced magnetic field opposes the change in flux. Induced B opposes the change in flux. If it didn't, if it supported the change in flux, you'd have a runaway process in which you would get an ever increasing EMF, okay? And that would violate conservation of energy. So just as the current, when we're pushing that thing, we felt the resistance to it, we can also say the induced B field is opposing the change in flux. So yeah, maybe you should write this out and not just with the symbols. This is called Lenz's law. Lenz's law. And the perfect example is, again, this model up here. So let's imagine we've got a conductor and we've got our B field through here. And what we're going to do is imagine that B is increasing. So it's increasing into the board. So the change in flux is that there's an increasing flux with that direction into the board. And what's going to happen, to oppose that change in flux, we have to get a counterclockwise current. And you'll remember the rule, if you wrap your finger around that current element, then thumb is the direction of the current, your fingers are curling in the direction of the B field. So inside here we're going to have these induced B fields opposing that change in flux. And of course outside they're like that, but the flux was determined for inside the loop there. So my example here is if B increases into the board, then I, here we'll use colors, counterclockwise produces a B field that opposes, okay, produces B field opposing the change in flux. Okay. So that's Lenz's law. And again, in your lower division book, you'll probably find a bunch of examples of this and questions of this type, little brain teasers and stuff, but that's basically what's going on there. The opposite of Lenz's law would be a runaway process that would violate energy conservation. Good. Induced current. So that's Lenz's law. So what we're going to do next is take this Faraday's law and write it down formally as a differential equation. Right now we had flux on one side and EMF on the other. We want to convert it to a differential equation. We're looking to get all the differential equations of electricity and magnetism by the end of this chapter. So what do we call this here? Faraday's law differential equation. The differential equation. So we'll start with what we had here. The change in flux is the EMF. I think I have the EMF as the change in flux. Okay, so yeah, we start with minus d phi d dt, and we plug in our definitions that we've had. So actually we'll just stack them. So here we have E dot dl, and that would be the boundary of an area, which is a curve. So it would be minus, and we'll go ahead and take the time derivative for the boundary is going to be not moving but fixed in this case. So we've got an area, and we have the minus sign, and we have B dt dot the area. So those are vectors. Okay. Flux integral through an area, and this is the curve that bounds the area. So we have to make these the same on both sides, same type of integral. And this is a length element, so a line integral. So good. The next thing we're going to do is apply Stokes' integral theorem. And then we have, transforming this side, we have the curl of E dotted into this area. You can also write n hat dA without the vector on it over this area. And on the right side we have minus d dt, same as we had before. Okay. So now that's both over some area, and I'll also stress that this is just an arbitrary area in the space over which we're investigating this, so that we can bring them under one integral plus dB dt dot the area equals 0. And now it's the old argument that we have all over the place, variational calculus, etc. Because this A is arbitrary, we can require that the integrand vanish. Okay, arbitrary. Therefore, integrand vanishes equals 0, and then we can actually write down, this is going to be one of the Maxwell's equations, this differential form of Faraday's law. Okay, great. Put it in the box. And differential form of Faraday's law. There we have it. Okay. So we're going to do a couple of interesting applications of this now. Okay. What we have is an induced electrical field. So we'll go back to we'll use the integral form and the differential form as we need them. But we already have a set of equations now. We'll put them all up that are related to or analogous to what we had with Ampere's law. So let's go ahead and look that up, or write that down, I should say. Because we can use the similar calculational techniques with these expressions here. So let's go ahead and put those up. So next, we'll just call this the analogy to Ampere's law. Which didn't actually have the time dependence there, but let's go ahead and write this down. So we have what we've just written down. We'll summarize that. We've got the curl of E minus dB dt. And that is, of course, equivalent to this expression here, flux. We have divergence of E equals 0 if there's no charge present. Okay, so that's Faraday and Ampere, so this is Faraday. Ampere, we had something similar. Okay. We had curl of B was associated with the current density. So we had mu naught J, current density. We had an integral form of this, integral D dot dl, and we used these symmetry arguments. So around a loop was equal to mu naught I passing through the loop. And here we had divergence of B was always 0. So the same type of arguments and techniques we use solving this set of problems, we can go ahead and use up here, because we can just replace these symbols one with the other. So if we have the appropriate symmetry, we can use the same type of arguments. So put that in words. So we can use symmetry arguments as we did with Ampere's law. Ampere's law. Okay. So the nice example of this, which looks just like an Ampere's law problem, but we'll have a B field instead of a current, is, let me see, I'm going to do this loop going to do it in profile and top view. So here's our loop. Say we got a conducting loop, and we've got B field pointing through like that. Or for the top view, we're looking down on it, we've got the B field coming out at us. Okay. So let's just evaluate Faraday's law. So we're just going to take the left side and the right side here. We're doing the integral. So we have, I'll work right under here. So here we have this E not dl integral right up there. And that's got E times 2 pi s. I didn't put the radius in here. Radius was s. E times 2 pi s on the one hand, and on the other side, the time derivative of the flux. So we're going to keep the boundary here constant, so we've just got minus pi s squared for the area, and then dv dt. So it depends on whether the magnetic field changes. We're keeping a fixed geometry there. Okay, good. So far, so good. So we cancel the pi, and we can get the E field. So right now we just have its magnitude. We're not even arguing about the direction yet. So we got the E field, cancel pi, we end up with S over 2. So we're going to keep our minus sign there. D, V, dt. So what about the direction? Now Lenz's law is what we would use, but I'm going to go ahead and put in the directions by hand. This doesn't get the direction, this just gets a magnitude. So the direction is just going to be phi hat, the minus sign, phi hat. And as you remember, phi hat is referring to this picture, counterclockwise directed, okay? And so, check. We'll check this. If dB dt is increasing, okay, let so dB dt be positive, okay, then the E field is apparently minus phi hat, which would be clockwise, okay. But you can see from this picture, if the B field is increasing coming out of the board, then we need a clockwise current according to Lenz's law to oppose that change in flux. So then E vector is proportional to negative phi hat, and that checks out. Good. So I have one more related, very nice example. I'm going to consult the clock right now. Okay, this will work perfect. So the last example actually leads to something completely unexpected. So I'll just clear a board and good enough. And, fill this in. In fact, I can draw my picture right here. So the final example, finally consider a non-conducting wheel could be some kind of wooden wheel. I'm going to draw it here. Attempted profile of radius B. Okay. So let's imagine we've got axle here. We've got, who knows, maybe some wooden spokes. Don't want to complicate things. Okay. But it's a wheel. It's non-conducting, and the point is there's going to be some charge on the outside. Make it blue. Since it's non-conducting, this charge doesn't move, it just stays put. With charge, line charge lambda on the rim. Okay, so that's the scenario. Then you have, so within a radius A less than B, you have a magnetic field. So the radius of the wheel is B. This inner area has a radius A, and there's some magnetic flux coming through here. Magnetic field uniform of strength B0. We'll write down what happens next. The uniform, or the initially uniform B0 initially uniform B0, as given by the red arrows, vanishes, okay? Decreases to zero. At some time. So at some time it's like this, and then we dial it down to zero. And of course that's a change of flux through this red circle here. And it's going to cause a corresponding EMF. But since this, since it's a non-conductor, the charge here, the blue circle, can't actually move unless the entire wheel moves with it. Okay. So because this is kind of a Lenz's law thing, because charge on a non-conductor, as the charge is on a non-conductor, the wheel itself must begin to rotate, because that'll give us a current, right? If the wheel itself rotates, we'll actually have a current. The wheel itself must rotate. Okay, so having set this up, let's draw some conclusions from that. And see how it happens. So we'll actually write down, Faraday's law and do the analysis. Okay, so let's just start with Faraday's law. So first of all, Faraday's law, and then plug in what we get there. So yeah, we have induced E field DL going to be actually d phi dt, but that's easily written down because the area for the flux integral is just pi a squared, and then b is changing, so that's dp dt. So that much we have, okay? So the next thing is that there is a torque. torque on little element dl of the perimeter on the blue part there is d tau vector is r cross f. Okay, that's the torque. Magnitude-wise, we're going to have the radius b, and then the charge will be lambda dl, and so that charge times E is going to give us that force. So there's the magnitude of our torque, and of course we can integrate the whole thing around the wheel for the total torque. Okay. But you'll notice these are just two constants, and otherwise we have our EDL integral that we had before. So what we get is the total torque is that integral with lambda b, and then we've got our E dot dl again, and that's lambda times b, so it'll be lambda times b on the right side as well. So minus lambda times b pi a squared dB dt. So now what we have, this is really interesting, we have a torque as a function of this geometry and stuff, and the change of the magnetic field. So, well, I got room for another line here. So, important to note, if we integrate, well, where should I put this? There's a relation between angular momentum and torque. So, recall that torque is equal to d angular momentum dt. So that L will be the integral of torque dt. That will give us the total angular momentum, and the amount of time it's going to be is for this, the time it takes for this B field to decrease. So we'll put that in at the end. So what we're going to do is integrate both sides of this equation. So what we have is L, referring to this important thing here, we have a total amount of angular momentum is going to be this integral with respect to time of this thing. So we've got our minus sign, we've got our lambda b pi a squared integral dB dt over dt, total angular momentum, and let's continue this over here. I'll keep the picture and erase this. And yeah, we can just keep going. Equals minus lambda b pi a squared integral dB from b0 to 0. Okay, that's good enough. And so what we end up with is angular momentum, all these constants here. This is going to kill the minus sign, so this order of integration, get rid of the minus sign. So we end up with lambda b pi a squared b0. See, that's what I'm supposed to have, yes. Okay. So this is an interesting model idea. And the thing is this wheel was at rest when we started. We just dialed down the magnetic field and now it's rotating. Okay. So does that violate conservation of angular momentum? If all we had was mechanics, we'd say yes, right? Because it started rotating. But what we find, and what we're explicitly going to find in the next chapter, this is just an example of it, is that the magnetic field actually possesses angular momentum. And when we dialed down that angular momentum, the total angular momentum was conserved because it went into this wheel here, interestingly enough. So let me just put that down in one or two words. Do I have any words for that? Yeah. So not a violation of angular momentum conservation. Conservation, because the field has conservation. Because the magnetic field has angular momentum. And that'll be discussed in chapter 8. So it's really nice to find this example here in chapter 7, because then, you know, we'll get the formal reasons for why there's angular momentum. Here it's just an interesting calculation that if you take everything seriously, you have to come up to the conclusion that you generated this angular momentum, and we'll learn next semester that it was in the field. It was in the field. Okay, consulting the clock once more. I was going to say a couple of words about the homework problem. Back in my section on motional EMF, I kind of skipped that, but I can do that now. So we had that list of homework problems. I'll put that down there and see what's been dealt with now in the course of these first 2 hours. Let's see what we had. So homework problems, these were chapter 7. Consult here. What did we have? I said 1, 2, 3, 5, 7, 8, and 11. 1, 2, 3, 5, 7, 8, 11. Okay, I wasn't going to necessarily insist on all of them, but let's see here. These were pretty basic. Oh yeah, these were great. So 1 and 2 with the charge capacitor. I didn't say anything about 3. I don't know if you guys have done it already. I can drop that from the list. And then 5 was the one with the battery and the EMF and internal resistance. And yeah, so this one I discussed a bit. Now problem 7 is a nice one with the motional EMF. You could say it's really just the other version, you know, kind of the other version. So 7, yes, problem 7 here So the motional EMF in this case is here's your circuit, and I think we build in a resistance here, and instead of pulling the circuit out of the magnetic field, we slide a bar across here. So it's really the same analysis that I did with, a little different, slight difference. So we're going to slide this bar across at speed v, and it's really almost the same analysis that we did. You're going to generate a current. You're going to talk about the current that's generated with respect to the magnetic field that's, in here, and you can talk about the flux rule, or you can just do it in terms of the actual forces. Works both ways. So yeah, that's almost it's a very similar problem. So that's a good one. So definitely keep that one. Problem 7, 8. Also good. I'm just very basic. You have to do a little integral. So 7, problem 8. You've got a current carrying wire. I'm going to assume like this, and you've got a loop here, and you want to calculate the flux through this. So you got a little integral because it's 1 over distance. Okay, the strength of the field 1 over distance. And then the question is, if you drag this thing away or push it towards the wire, what current is generated, what EMF, and so forth. And you use Lenz's law on that one as well. Definitely comes out nice. Yeah, so these two are good. Do those, and that's 8. Actually, 11's good too. Yeah. I'll leave those all up on the assignment. See how you guys do. I'll get some feedback on Friday whether you did them all or not. But we'll keep all of these on our plate. You can ditch number 3, 1, 2, 6, and see how it goes. Okay, good. That'll be that for now, and see you guys next time.